In this video, we're going to talk about something that, while not imperative that you know, might save you some time. So, what I'm talking about here is special products of polynomials. When you multiply two polynomials together, which you already know how to do, the kind of weird results that we get, some patterns that we can use in the future to help us out. So, here's what I'm saying to you. Do you absolutely have to know about special products? No, not really. You can use your standard distribution and figure out all this stuff. And I'm going to show that to you. But if you notice some special products, we can sometimes use some shortcuts. And that's okay to do as long as we understand the nature of them, why it works the way it does. That way we don't make mistakes on them. So let's look at a few of these. This is going to be a quick video. We're going to spend a whole lot of time on it. I'll just show them to you so that you can identify them and appreciate them. Let's look at what happens when you multiply two terms that look exactly the same except for the sign between them. Let's see what really happens here. You see, if we multiply these together, we should get a squared, we should get plus ab, we should get minus ba, but we learned that it doesn't matter the order in which you have your terms factor in our terms. So we could get minus ab or minus ba, and it doesn't matter. And lastly, minus b squared. We know how to distribute. We know how to take two terms times two terms. You can use FOIL or think of monomial times several terms in a polynomial and do it twice. Either way, we get a squared plus ab minus ab. Notice ba and ab are the same exact thing. And minus b squared. And what happens is that your middle terms will be exactly the same with different signs. They'll always work that way if you have this scenario. And what we're left with is a squared minus b squared. In future videos, we're going to call that a difference of squares. And we'll actually go backwards and use this exact technique to factor it, going in reverse distribution. But right now, we're noticing a couple things. If you ever wanted to distribute two terms times two terms where they have different signs, basically, you just take the first two terms, multiply it, last two terms, multiply it, and put a minus between them. If those are different signs, then that's always going to be a minus. Verify that. If it's a minus, that's a plus. Negative times a positive is a negative. Plus and a minus, positive times a negative is also a negative. So, let's look at the next one. It looks pretty fantastically ugly. But if you were to distribute this, you have the same exact two terms, but the second one has a different sign. Does it fall into this pattern? Yeah, that's exactly what we're talking about. Now, just so that we're clear, could you literally just go through and FOIL and get the same thing that we're getting? Yes, and that is fine. That's perfectly fine. But if we're understanding that this pattern works, and we're understanding that the middle terms here are going to cancel, then we can take the first two terms, the last two terms, and we're done. Multiply the first two terms, multiply the last two terms, and put a minus between them. And that will satisfy your distribution. It's going to be exactly the same. You see, if we multiplied this through, we'd have 4x to the fourth, no problem. We'd have plus 10x squared y cubed, and we'd have minus 10x squared y cubed. Those middle terms would cancel, and then we'd have minus 25y to the sixth power because we're adding those exponents, not multiplying. And you're done. That's what special products are used for. It's for when we have certain cases, special cases of multiplication, that we can quickly and efficiently perform that operation. Important to know? Useful. Imperative to know? No, it's not imperative, because you can get the same thing through distribution. Now, I will tell you this, though. It will help you in your factoring if you're used to these forms. If you know what the product of this looks like, you're more likely to understand what the factoring of this is going to look like as a product. Now, next one. These are the biggest ones, because this is where a lot of mistakes come from. This is what I need you to get in this video, is that exponents do distribute. Stop. Exponents do distribute across one level below their operation. Exponents distribute across multiplication, not two levels, addition, subtraction. Exponents never distribute across addition or subtraction, ever. So in no way, shape, or form is this ever equal to a squared plus b squared. That does not work, and it's not going to work there either. It's not a cubed plus b cubed. I wish it was, man, I wish it was that easy, but it's not. In fact, when we think about what a plus b squared means, it really means not that. I mean, no, that was. A plus b times a plus b. Exponents mean repeated multiplication. So that's what a plus b squared means. Now, if we distribute this much like before, but look at the difference. One of them has different signs. We actually call that a conjugate later on in math. Two terms, different signs in between them. And these have the same sign by the nature of them being from the same exact expression squared. If you distribute them, sure, we get an a squared, and we get an ab, and we get another AB. B times A is the same thing as A times B. And we get a B squared. And your middle terms are still like terms as they are here, but they don't have different signs anymore, which means they're not going to cancel. They're actually going to make two of the same term. So we get an A squared, we get a two of those guys. Those are like terms, 2ab, and we get a b squared. Notice how it's not just a squared plus b squared. If you do that, you're missing that entire middle term. That's a problem. Now, how's it used? Could you do with this exactly the same thing with what we did here? For sure. You could do 2y plus 4 times 2y plus 4 and be golden. However, if you notice the pattern, what this says is you square the first term. Square the first term. Square that term, you're going to get 4y squared. Square the last term. Square the last term. That's going to give us 16. In the middle, multiply these two terms together and then multiply by 2. Multiply the two terms together, right there, and then multiply by 2. So if I multiply these two together, I get 8y, and then if I multiply them by 2, I get 16y. So this 4y squared, multiply them and multiply by 2, 16y, and then this squared. Is it really the same? Let's see. Let's see. 4y squared, it's there. We'd have an 8y and another 8y. That's why you multiply by 2, because you get the same exact term twice. 16y and then plus 16. So it is the same. Useful? Yes. Imperative? No. But it's kind of cool to see those patterns. Also, this is called a perfect square trinomial, and when we get to factoring, coming up here real soon, when we factor this, we're going to get right back to that, which is kind of cool. Now, what if it's not a plus but a minus? Honestly, the same exact thing works. Square the first one, square the second one, multiply them together, and multiply by 2, and it'll be fine. So here we'll get 36y to the 4th. If you square that, 6 squared is 36. Y squared squared 2 times 2 is 4. I'll square this also. Notice when you square a negative, you will get a positive, though. That's got to happen. So negative 5x squared is positive or plus 25x squared. In the middle, multiply these two. So that's negative 30. Notice how it's a minus now. Negative 30xy squared times 2. That's negative 60xy squared. That will be the final answer, using the exact same technique. So here it is if you really need to see it, like the proof of it worked out. If you change this to a minus, then that's also a minus. That's also a minus. But a squared is still a squared, and negative b times negative b is still plus b squared. It's just that these two signs would both change to minuses, and that's exactly what we're doing here. If you want to write it out, you certainly can. It's not even a big deal. But this is where our 36y to the fourth is coming from, right there. This is minus 30xy squared, another minus 30xy squared, that's minus 60, and then plus, notice negative times negative, plus 25x squared. Exact same thing, using our patterns, using our formulas is just a little bit quicker. Now the last one. I would love to tell you that there's a nice, easy formula to allow you to distribute this correctly and be fine. The one thing I can tell you is this. Don't distribute that 3, I'm begging you. You see, when we distributed, it was on stuff like this. Exponents do distribute, but they distribute one level below their operations. If you're learning anything from this video series, it's that on exponents, is that the exponent rules always work one level below. It's always one level below. So how do you distribute exponents? One level below. In fact, distribution is a concept of one level below. When you distribute multiplication, it's across addition, subtraction. When you distribute exponents, it's across multiplication and division. So sure, this exponent does distribute across multiplication. But this exponent can't also distribute across addition and subtraction. That makes no sense. Exponent rules have to apply in their specific cases. So this stems from the misunderstanding of this. That's where that stems from. So let's get this right. Exponents do distribute across one level below, multiplication. Multiplication distributes across one level below, addition, subtraction. Exponents do not distribute 2 levels below. They do not distribute across addition, subtraction. This is blatantly wrong. We can't do that. So what do we do? Well, you write it out, and you think about what repeated multiplication really means, and this is a plus b 3 times. Now, how do you work with that? Here's just some advice to you. You can do this however you want. It's just distribution twice. I do, this is the way I do it. I ignore the first one. I distribute the second two. In fact, oh man, if you see the pattern, you could distribute this using, well, the first one I put with the plus. You could distribute this with that formula. That's okay. Or just distribute 2, combine some like terms. Do the last 2 first, and then distribute the first one. If you want to see that, I'll do that right now. That'd be using the first formula that I showed you. A squared plus AB and another AB. That's 2AB plus a B squared. Now, that's what that is. And you can distribute on your own if you need to check that out. Now, that's in parentheses because you're still multiplying this A plus B. If you multiply the A plus B through, now it's really just a distribution problem of 2 terms times 3 terms. We're going to get 6 terms and then combine. So when we do that, there's an A cubed, a 2A squared B, and an AB squared. Then I have my second term distributing through. I always write my terms in alphabetical order, so those factors are alphabetical. So that allows me to see like terms a little bit easier. So instead of BA squared, I'm going to write A squared B. Plus 2AB squared, and then a B to the third. So we do actually get an A cubed and a B cubed, but look at all the stuff we'd be missing if we just did that. I mean, that's silly. Now we'll look for some like terms. I'm going to write my A cubed first. The idea was, I talked about in the last video as well, we do like order for variables, but when you have more than one of them, choose one variable, usually the higher alphabetical order, and put that one in order. So I'm going to start with A cubed. I got that. I'm going to look for any other A squared B somethings that are the same. So A squared B and another A squared B. So 2A squared B and A squared, 1A squared B. That's 3. Now I have, well, I'm looking for a to the first power and then b to another power. So here's a to the first, b to the second. Here's another a to the first, b to the second. That's another 3 of them. And lastly, the one without any a's. That's b to the third. Now, I just can't leave this hang. I can't make it that far and not tell you this. By the way, that's it. I mean, that's as far as you go. A cubed, a squared, a to the first, no a's at all. That's in some relevant order. That looks really good. There's no other like terms. We're done. But I can't leave this hang. This is something that stems from binomial distribution, binomial expansion, which is really cool. There's this guy named Pascal, Blaise Pascal. He did a lot of stuff. But one thing he did, he came up with this thing called the Pascal's triangle. Which, if you look at it, you have ones, you get ones, and every pair of numbers in the preceding row, when you add them, adds to a term. So 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 2 is 3, 3 plus 3 is 6, 1 plus 3 is 4, 3 plus 1 is 4. And you can continue this just forever, as long as you want. Here's what's really weird. What's really weird. If you have binomials, which is a two-term polynomial, and you have, let's call that number n. Hope this blows your mind. Awesome. And you go to the first relevant row and the second relevant row. If you have a second power like that one, this will tell you the coefficients of your terms. So if you have to the second power and you have binomials being expanded like this, so a minus b to the second power, you're going to count how many terms you have. You have 1, 2, 3 terms. 1, 2, 3 terms. Here's the coefficients. 1, 2, and 1. 1, 2, what the crap? Different sign, yeah. But if I change it to a plus and change it back to what I had, 1, 2, and 1. Does it always work? Let's go to 3. This says you're going to have 4 terms. Here's your coefficients. 1, 3, 3, 1. 1, 3, 3, 1. That's like a mic drop moment. So wait a minute. If you wanted n to the 4th, you want to do that 4 times? Instead of going a plus b, a plus b, a plus b, a plus b, and distributing like 3 times, you're saying that you should have 1, 2, 3, 4, 5 terms. Yes, you should have 5 terms. 5 terms. Your first term should have a coefficient of 1, 4, 6, 4, and 1. Your exponents should be descending. A to the 5th. Oh, nope, that's wrong. That'll be the next one, sorry. A to the 4th. A to the 3rd. A to the 2nd. A to the 1st. No A's at all. Your exponents for B should be increasing. No B's at all. B to the 1st. B to the 2nd. B to the 3rd. B to the 4th. And we have all pluses. All pluses. If you had minuses, they'd be alternating. That's crazy. That takes care of distribution all at one go using Pascal's triangle. And that's way beyond this class. Okay, well, where you're at right now. But that's freaking cool. Because when you get to calculus and you have to actually do that for like a plus b to the 5th power, you are not going to want to do that 5 times. Yet you can easily go, oh, let's see, it's power 4. Here's 4th row, Pascal's triangle. I don't know why I sound like a nerd right now, but 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. A is descending, A, so 4, 3, 2, 1, none. B's ascending, 1, 2, 0, 1, 2, 3, 4. Done. Completely expanded. That's awesome. That's where some of that advanced stuff comes from. Anyway, I hope that was interesting to you. I hope you hung out and kind of watched that, because that's pretty cool. I will see you guys for the next video. We're going to talk about negative exponents. That's a complete, like, Nah, you're messing with me moment. But they exist and we'll talk a lot about them. I hope it was fun for you in this video. See you next time.